This video will focus on the learning target. I am able to identify and determine relative strengths of acid-base conjugate pairs. When talking about acid-base conjugate pairs, we'll be using the Bronsted-Lowry definition of acids and bases. And just a reminder, acids then are substances that have a hydrogen available to donate, and bases are substances that have a hydrogen available to accept. So what is a conjugate acid or base then? Well, basically, every time an acid exists under the Bronsted-Lowry definition, it is a substance that can donate an H. And when it goes through the process of donating an H, it then becomes what we call conjugate base, because that substance could take back on that hydrogen in the reverse process, thus making it a base. Vice versa, every substance that is a base that is able to take on a hydrogen, once it has taken on a hydrogen, becomes what's called a conjugate acid. So a conjugate acid is one that once it has accepted that hydrogen could redonate it off in the reverse direction. So depending on the acid-base situation, these are equilibrium reactions, in which case depending on the direction it's proceeding, some substances could be an acid in one direction and a base in the other. So the way it'll work then is every base will always have a conjugate acid, and every acid will always have a conjugate base. They'll always have a pair that can go together depending on which direction we are going in. The other part of this target is to understand the strength. And essentially, the stronger one substance is, the weaker its conjugate is. So to clarify, here's some charts of acids and bases. And if we just take that first one up top on the acid side, that perchloric acid, HClO4, that's an acid by definition because there's a hydrogen available to donate. If it goes through the process of behaving like an acid and donating that hydrogen, it would make the chlorate ion, which is on the other side of the table, right? We would define the chloric acid as an acid, and the perchlorate ion, it's the base that was created by the acid, and now if I go in the reverse process, it would become a base. It would be able to take on that hydrogen again to become perchloric acid. Based on this chart, you can see that the perchloric acid is the strongest acid that exists, which means the chlorate ion is very weak. So the stronger the one substance is, the weaker its conjugate is. We'll talk about strength at a future date, but just that relationship is something you have to understand. So if we look at something more at the bottom of this table down here, like the hydrogen carbonate ion, for example, HCO3 with a -1, that has a hydrogen available to donate, and when it donates that hydrogen, it becomes the carbonate ion, CO3 - 2. That's its conjugate base. Now, because that HCO3 is not very strong, the carbonate ion is stronger. What that really means is based on the equilibrium shifting, we have more of a tendency for carbonate to act as a base than for that hydrogen carbonate to act as an acid. So really the strength is indicating the direction of shift. Perchloric acid in water will tend to give up its hydrogen. It's a very strong acid. But the perchlorate ion is not a strong, very strong base. It's not going to take those hydrogens back on. Where if you had the hydrogen carbonate ion in water, it's going to tend to stay that way. Where if you put the carbonate ion in, it's going to tend to try to find H's to bond to. We can go either direction on this table. I'm using acids as my example, but for example, if I had the base ammonia, NH3, that would be called my base. It has a conjugate acid with it, right, the NH4+. So it just depends on where we start and where we're headed to whether we call it an acid or a conjugate acid or a base and a conjugate base. But essentially, we think of these as pairs, right? So we have an acid and base that have a pair where depending on whether I'm giving up the hydrogen or taking it on, they go together. So if we look at this particular reaction, we have two substances, and from start to finish, there is a hydrogen being transferred. Okay? So when I look at an example like this, the questions that are asked are for you to label what's the acid, what's the base, what's the conjugate acid, what's the conjugate base. So I always look at my two reactants, and I look at them as it compares to product, and I say, what happened? From start to finish, did it add a hydrogen or did it give up a hydrogen? So that HSO4- substance, if we look at it from start to finish, it had a hydrogen and then it didn't have a hydrogen as a product. So that acts as an acid. Acids give up hydrogens. So I would label that HSO4 my acid, and the SO4- 2 then as my conjugate base. So if that SO4 went in the opposite direction, it would take back on that hydrogen, meaning it's a base. So every acid makes a conjugate base. So that in the reverse, taking back on that hydrogen, it acts like a base. H2O in this case is going from H2O to H3O plus. It's taking on a hydrogen, so H2O is acting as a base, and that H3O plus then is the conjugate acid. Another example here, same 4 questions. When I compare the NH3 to NH4 plus, I see that I gained a hydrogen, so that would be a base. NH3 is a base. In the reverse direction, NH4 goes back to NH3. It gives up an H, so that's an acid. So NH3 is the base, NH4 plus is the conjugate acid. H2O in this case is acting like an acid because it donates an H and it has just OH by itself in the end. So the OH is the conjugate base. What you see in this process essentially is they're transferring, right? The H3O plus gains a hydrogen from the water. So in the end, the hydrogen is just moving locations. That's really what a Bronsted-Lowry conjugate acid-base pair is. It's understanding that when they go together, there's a transfer of hydrogens, and so we have lots of acids and bases present, depending on how we look at it. One thing of importance is if you notice these last 2 examples, in one example, water, H2O, ended up taking on a hydrogen, thus acting like a base. And in this example on the screen, water ends up donating a hydrogen, thus acting like an acid. So there's some substances where we look at them, they could do both. They could both take on a hydrogen as well as give up a hydrogen. And we would call those substances amphoteric. So amphoteric are substances that can act as an acid or a base depending on conditions. Now, we'll practice this more, but how you know whether something will donate a hydrogen or take it on is going back to kind of your foundation of Bronsted-Lowry. So if it has a hydrogen listed out front, it's an acid. And for bases for Bronsted-Lowry, in order to take on a hydrogen, you need to have probably a negative charge, or this nitrogen group, the ammonia group, tends to take on a hydrogen. That's it for the foundational concepts of conjugate acid-base pair. Go ahead and do the quiz and have a nice night.